One last example of applying the failure criteria, and we're going to look at a pressure vessel. Now, again, the reason we're doing this is that sometimes if you predict a failure of a single layer, it may not mean that the total laminate is going to fail, and pressure vessels are a good example of that. So we'll say this cylindrical pressure vessel, nominal diameter 12 inches, balanced plus and minus 15-degree helicals, total thickness of 1/10 of an inch, 90-degree hoop layers, thickness of 0.15 inches. And so we want to predict what internal pressure is going to cause the vessel to burst. So first of all, let's just arbitrarily pick a pressure of 1,000 psi and calculate Nx and Ny. Hoop will be 6,000 pounds per inch, axial will be 3,000 pounds per inch. And we'll calculate the stresses. There we go for the plus and minus 15s, and there you go for the 90s. Now, one thing you notice is that all the layers are in a state of biaxial tension. And we can also calculate the factors of safety there. And we can see the factors of safety just slightly below 3 for the plus and minus 15s, and a little bit more than that for the 90s. So we're predicting that we have failure at 2,990 psi internal pressure. And again, if I now analyze at that pressure, of course we're going to come up with a factor of safety of 1 for the plus and minus 15s, but the stress state, as you can see, is shown here. Now, sigma 2, remember the strength in that direction is 7,000 psi, so we do get a little biaxial improvement, we would call it, but that's what's causing it to fail. Now, the Saiwu criterion, remember, is just a single interactive criterion, but it's been proposed that you can actually look at it as being 2 criteria, one for fiber failure and one for resin failure. So if we take just the ones that are associated with the fiber direction stress, sigma 1, and call that the fiber component, and take the rest of them, which involve the shear stress and sigma 2 and the interaction, and say that those are indicative of a resin, then we can predict what's going on when we reach that that predicted failure. I'm going to shift over to spreadsheet, and so here we put it in at 1,000 psi with the 3,000 and 6,000. There are our factors of safety. Now what I want to do is we'll just ratio these up by that factor of safety. So 2.99 being our factor. And so there we see the stress state at the predicted failure. Now if I move down here, what I've done is added those fiber terms and resin terms. So you can see that this would indicate that, hey, the fibers aren't breaking here. It's just the resin that's failing. And the resin failure, it may not be, in fact usually is not going to be a catastrophic failure. So how do we deal with that? Let's go back and remember that instead of assuming that the laminase fails, we're going to degrade the layers that have the predicted resin failure. And so in Tsai's book he proposes this degradation factor, and rather than trying to calculate what that is, we're going to just take a ballpark at it here by just saying that when we get rid of the resin's component, strength component there, then it's not going to be able to resist load in the 2 direction. Certainly the Poisson's ratio will come close to 0, and it won't actually be resisting any shear as well, so G12 will come close to 0 as well. Now sometimes if you just make those exactly 0, that can result in some numerical problems, so I'm going to just set them to very low values. So we really are again discounting the stiffness properties of the resin by doing this. Now, I really don't need to modify the strength values because the low stiffness means that I'll end up with really low stresses. However, it's possible that you'll have a fiber in compression And if that's the case, again, SIA recommends you don't get rid of the compression strength altogether. The fibers are still intact, but without the resin around them to prevent micro buckling, you should degrade that strength as well. Again, it doesn't really, not going to make any difference in this problem because everything is in tension. But going along with that, we're going to look at what we would call a degraded layer properties. And so we're going to reduce, as we said, E2, nu12, G12, and we'll also reduce the compression strength in the fiber as well. All right, so what I'm going to do, the way I'm going to accomplish that in the spreadsheet, is I'm going to go over to the materials page, and you can see here I now have degraded carbon epoxy as a new layer, number 7. And you can see again 100, 0.01, 100 as well. And the strength down here, compressive strength, been reduced from 150,000 to 90,000 psi. All the other properties staying the same. Okay, now we're back, and once again, now we've said the 15 and plus or minus, the plus or minus 15 layers are going to fail due to the resin. And so what I'm going to do is change the material code to be the degraded carbon epoxy. And now let's go back and run it again at 1000 psi. And see what we get. And so yeah, you see that, hey, sigma 2 and tau 1, 2 are 0 now because again there's no stiffness assigned to the resin. And now the failure is predicted to occur at 3.31, in other words 3310 psi internal pressure. Okay, so let's increase the loading to correspond to that increased pressure, and now we see, okay, now we got the factor of safety of 1 as we see. But also again, notice that this sigma 2 is pretty high compared to the strength value of 7,000. And again, when we look at the terms here, this is going to be a resin failure. And so now we can degrade that layer as well. And once again, to make it easy for comparison, we'll go back and put the 1000 psi on here again. And we see now that our critical factor of safety is 7.78. And of course, well, if I increase to 7.78 to show what the stresses are at the predicted failure, then I get the factor of safety of 1 here. So, and you see, by the way, the sigma 1 is, within a little round-off error, is the tensile strength, 300,000 psi. The plus or minus 15s are slightly over-designed, but you see that essentially we've only have stress in the one direction. So sometimes this is called netting analysis, which is done for pressure vessel, where you ignore the resin altogether. And again, you see here that our fiber term, the failure is totally due to the fiber because, of course, the resin's not picking up any stress at that point. So once again, we degraded the plus or minus 15s, ran it again, found that the critical factor of safety now is the 90s. We degraded the 90s, and so there were our factors of safety with everything degraded. And so we can now kind of predict how failure is going to occur. That is, when we get to 7780, that's when we're going to have fiber failure, and the vessel will be burst at that point. So we've kind of got a map of how that's going to work. When we get to about 3000 psi, we're going to have the helical resin cracking. A little bit above that, then the hoop layers start to crack. So that when you actually do a test with this, you'll see it's pretty noisy around that. Then it kind of gets quiet again because the resin's all cracked. And then, at a pressure even double that is when you finally get burst. Now I mentioned, you hear the resin cracking. There's a process called acoustic emission testing. And if it's a critical application, a lot of times you'll evaluate the sounds that are being emitted from the vessel, because fiber breaks, delaminations, resin cracking, they all have different acoustic signatures. And so sometimes you can detect manufacturing flaws, or if it's been in service for a while, accumulated damage during a pressure test. Okay, so one last comment about failure criteria that we mentioned at the very beginning is that there is not a failure criteria out there that's been shown to accurately predict failure for all materials in every loading condition. It's still very useful to know this for doing preliminary design, for comparing designs, but always keep in mind that certainly if this is a critical application, you have to do physical testing to confirm those calculations. And with that, that wraps it up for failure criteria. And so getting ready to start the next section, in which case we're going to look at bending.